Okay, hello everyone. I'm here to present this article, Use at Your Own Risk, the Java Unsafe API in the wild. So if you before saw that Java was a safe, so Java, we think that Java is a safe language. It has a type safety, it's memory safety. So so in theory, if I have a small program, a Java application, the usual way to report an error is through exceptions. So I should never get a crash from the JVM. So if I have this small program, oops, I have a crash, but I crashed the JVM. So everything that I thought that was safe in Java, it doesn't happen anymore. So what's the problem here? Or why I got this problem? And the key is here, unsafe. This unsafe word here refers to the class, to a class, sunmiss unsafe. But what is it? What is this class? This class is a class added to the JDK to improve the performance of the JDK itself. It allows the developer to access low level. It has a low level. It allows the developer to do low level operations, and also to do operations closer to the hardware. But as you can see, it starts with sun. So in theory, this class shouldn't be used. Probably at some point when you develop in Java, you may encounter this web page that says you shouldn't use any class in some packages. Moreover, people who develop Unsafe, they try to hide it. They try to hide it in a way that if you want to use it in your own application outside the JDK itself, you need to do this kind of hack. This is only one hack where you can use Unsafe. So you might be asking now, okay, in theory, you are not supposed to use it. Then it's hidden. So what kind of problem do we have here? Ouch! This is a crash, a bug report from Elasticsearch due to Unsafe. Another one, Hazelcast using Creo, another crash. This is, I want to emphasize this, it's not only an exception, this is a crash. You crashed the JVM, so when an application you have run on that JVM, bye-bye. So, you have also, due to Unsafe, then a Snappy that is in a library, the same. NetBeans, you have in this case you have an error. Also, maybe I don't know, it's readable, also because of Unsafe. So in here we need to ask, okay, now apparently there are some people over there using Unsafe. So do we need to care? So apparently the main point here is Java was safe, apparently now it's not safe anymore. The goal of this work is to try to work in the direction to make Java safer. For that, we want to know. Okay, now we have like 4 examples, but who else is using Unsafe? So our first question that we need to ask ourselves is, Unsafe, is it used in common application code? So what is the impact of Unsafe in the real world? So for the real world, we chose the Apache Maven central repository. We think that this repository is a good example of what is real code, because a lot of projects, and not only in Java but also in other languages like Scala, deploy to the central repository. So this repository has around like 900,000 artifacts. An artifact is basically the output of a build, nothing else. And this is around 1.7 terabytes. So this was also one of the key points. We choose Maven because Maven Central, because it's one of we think that it's the largest Java repository. But the artifacts are versioned, so we are not interested in each version. We are only interested in the last one. So if of those initial artifacts we take the last version, we have like 100,000 artifacts. But since our analysis is based on compile archive bytecode, it's not done in source code. We only are interested in jar files, Word file, and ER and HEV, and all kind of files that are bytecode itself. So after this filter, we have analyzed 86,000 artifacts. That is 86 jar files or Word file, like compiled archive bytecode. And this is around 74 gigabytes. So after our analysis looked for static usages of some is unsafe. We found 800 unsafe artifacts. That is around only 1%. So at this point, it's like we don't have any problem. That's it. It's not so much. But then we ask ourselves, what is this 1%? So who is in fact using some is unsafe? Oh, sorry. And then we have for this we found that there are like 48,000 call sites and 300 field accesses. This is the thing that we found. But we want to know who is using some is unsafe. And we start to see, okay, we have some languages like Scala and Ruby. That's fine, because if you trust the JDK developers as a language, you also trust the developers of Scala and JRuby. But then we found some frameworks like Spring and Hibernate, or maybe some serialization libraries like Genesis or Xstream, database applications like Cassandra and Neon4j, concurrency libraries like Akka or Netty, and big data like Hadoop and Spark. And probably you might hear at least of one of these. So if you don't know, you were using Unsafe maybe without knowing it. So then we know, okay, we think that these are popular libraries. So let's go back and try to make a parallel analysis. In Maven, all the artifacts declare their dependencies. So what if we take the transitive closure of the projects that are using Unsafe and see who depends on those? After this analysis, we found that around 21,000 artifacts depends on projects that are using Unsafe. So indeed, directly or indirectly, there are a lot of projects, a lot of people that are using Unsafe without knowing it, like 25%. So we think that this is an impact of Unsafe, so we need to do something. So after knowing, okay, now Unsafe is used, what feature of Unsafe are being used? In what way? So for this question, we try to, with the call sites that we have found, we try to group it by functionality of the method. So for instance, we can see that, for instance, the object field offset and the array-based offset methods are two methods that are heavily used, and they are in these two groups, offsets and array. These two groups allows the developer to query the memory layout either of an object or an array. Then, whether you with the offsets and array groups, you can have like a reference to a field or an element in an array. Then, with the heap get and heap put, you can read or write in a specific memory location in the Java heap. And then we have this cast and fetch and add that allows the developer to do atomic operation. This translates to it directly to machine instructions to do compare and swap. So, as I mentioned a bit before, now we know that offset and the cast group are the most heavily used. But on the other side, we know that the fetch and add group, it doesn't look like they are too much, that many people are using it. But the reason why is because fetch and add was added recently to the JDK. So, in fact, we can see that even that there is no almost no use of a group, we can see that people are looking at Unsafe and they want to use it. They want to do something. They need to do something. They need Unsafe. So now we know that there is an impact. Now we know that how Unsafe is being used. The main question that we want to know is why. Why people, why projects needs to do Unsafe? So let me show you. So to answer this question, we have analyzed those projects, most of those projects that were using directly Unsafe, and we found 14 patterns, 14 reasons why Unsafe is being used. So let me show you what the pattern is. So first we have a pattern called a process byte arraying block, and the idea here is instead of when you have to process an array, instead of doing it byte per byte, you do it in 8 bytes at a time with a long, let's say, right? So how does this work? This is an excerpt of a code. I don't expect that you read, but the basic idea is that this is an excerpt from Guava, a popular library from Google. And the idea here is that first you need to know where the payload of an array starts. And you can know this with beta array base offset. Then the key point is that with getLong you can get from the byte array you can get 8 bytes at a time. And the last part how this pattern works is you need to be sure that a byte is only 1 byte, but you need to make it sure. And this is, as you can see also in the comment, this is only a sanity check. So there are like 3 methods: the index scale, the base offsets, and the getLong. So we have a pattern using Unsafe. What's the problem here? You are assuming when you are using this pattern that the array is stored in a continuous manner, and this might not be true for some virtual machines. So you are losing portability. You need to be aware of the endianness of the virtual machine, because depending on the you need to take actions. Like also in the comments before, you need to take action if it's depending on the endianness of the machine. And as we will see later, it might be not the case that it always give better performance results. So this is something that it might work in principle, but you need to really test it on a different platform to know that this is the case. So let me give you another pattern. Atomic operation. Atomic operation allows you to implement non-blocking data structures. How it is done? The idea here, you can see that this compare and set helper function this is the LMAX disruptor library. It calls the compare and swap long method. So with the compare and swap will translate directly to a machine instruction that allows you to, even on presence of multiprocessor, you can do a really atomic operation. And this pattern works with one of the cast group or the fetch and add group. And also you need the offset. You need to know which variable you are modifying. So to get the value offset, you need the object field offset. So basically, the idea is you have an object, you know whether an object is placed in memory, and then you can do compare and swap on that particular field. Okay? The problem here is that, as with concurrency, it's really difficult it's really hard to get it right, and the developer needs to be aware of the memory, the Java memory model, how to interact, how Unsafe interact with the memory model of Java. So the last pattern I want to show you is update final fields. The idea is that you have, let's say, a string. This is from Groovy, and you can use put object and put in to modify final field. For this, you need also the offset, as we see we have seen before. Okay. The problem here is that you are breaking the language itself. You are breaking everything. You are modifying a final field that is not supposed to. You are not supposed to do this. What could happen that since the compiler might cache a final field, you can have unexpected results. This is also with free visibility. You need to be aware that other threads can see the updated value. Okay? So the other question that we want to know is, if now we have these patterns, what people is saying, what kind of problems do developers encounter when they are using Unsafe? To that end, we mine a Stack Overflow to analyze what people is saying about some is Unsafe. So we found like one of the most important things is that since some is Unsafe is not documented, we found that a lot of people asking how to use Unsafe. Then we found like there are other people coming from C++, coming from C++, want to use Unsafe to do the same thing that they were doing in C. They want to do it in Java. They wanted also to free memory. They want to free an object using free memory. This is the kind of thing that they want to do. So that's why we need to stop the Unsafe, this Unsafe thing, because it's really unsafe if they want to try to do this. And about the performance, as we saw before, there is a post on Stack Overflow saying that not always is the case that the processor byte writing block it's better. So when you use one of these patterns, you really need to know what you are doing. So to finish, what discovered here, that we know that there is an impact of some is Unsafe in Java. We know what features are being used. We know why people is using some is Unsafe. And also, we know what kind of problem do they encounter. So, what we have provided here is evidence in the evolution of. We provide evidence to make language decisions. This is to evolve the Java language, and we hoped that we can make the Unsafe safe. Thank you.